So those are your basic moments questions. There's different styles that they can come up in. You're going to have some kind of rod that is either supported from underneath by a couple of supports or held from above by some strings. These may then either be uniform rods or non-uniform rods. They may be perfectly in equilibrium, or they could be on the verge of tilting. And either way, we can therefore use expressions of vertical equilibrium and moments in equilibrium to work out and isolate certain unknowns to then give us information to continue forward with these scenarios. There is one other kind of question that contains moments though, and it's more under the purview of static rigid bodies, but I'd like to just address it here obviously while we're talking about all these other concepts. So if I may just keep you for a little bit longer, we'll now turn to these other two questions. Now already just by looking at these two diagrams you may start to think these are definitely different to before, because now the rods that we're going to be working with, they are at, if they're not at diagonal itself, then they have components that are at diagonals. It's not all perpendicular just with straight up and straight across. So let's read through the scenario first though before we start having to try to consider how we're going to annotate any of this. So we have a uniform ladder of mass 20 kilograms and length 5 meters is at rest, with end A being on rough ground and end B on a smooth wall, while being on the point of slipping. So based on this, find the magnitude of friction and theta, that angle between the ladder and the ground. Well, the difference with this when it comes to our working, therefore, is that some of your forces, if not all of them, are going to be at angles to the rod in question rather than perpendicular, so we're going to have to take components like we would in other static rigid bodies scenarios. Before we kind of can determine how we're going to have to apply those components, though, we'd better just start annotating as best we can. So we know that it's a uniform rod, therefore the centre of mass is going to be right in the middle. Therefore we can say that there's 200 kg, which would be a weight of just 200 times gravity, 20 times gravity, so 20g here. That would be acting at what is essentially a distance of 2.5 meters, if the whole thing is 5. Now then, if it's resting on the ground here, there's going to be a reaction force upwards from the ground at A, but also, just to differentiate things here, you're going to have a reaction against the wall B here, otherwise the ladder would be just pushing straight through the wall and falling through it. Now, we also, because the ground is rough, are going to have friction acting in the opposite direction to the desired motion. So if it's on the point of slipping, like on being the point of tilting, the thing isn't moving yet. It's still technically in equilibrium, but we're going to have maximum possible friction here. That which you would get from the coefficient of friction times by the reaction force. Again, if you want clarity on that, so that's covered in kind of like your static rigid bodies, so slopes kinds of questions there, or pulleys potentially. So in this case, if the ladder is going to be slipping, the base A is going to be slipping to the left, right? It's not going to be slipping closer to the wall. Therefore, friction will be going closer to the wall. That's opposite to the direction of desired motion. So friction is going to come this way. These then are going to be all of your active forces, right? So how can we try to make these perpendicular to your rod? Well, what we can do at each point where the force is acting is represent as a dotted line exactly where the perpendicular line would be. So these would be your perpendicular lines for the weight here and the reaction force, and then these here would be your perpendicular lines for the friction and for the reaction then up at B. To then just label on some angles. Actually, if we were just to continue this here, so it's more of a right angle. So what I've ended up doing here is making an angle in a right angle triangle that's here. because this line here and this line here would be parallel, they're both going to be acting in the same direction. Basically, this angle is going to be the same as your theta from here. Same as here, if we were to then continue this somewhat this way to make a right angle here, we could say that this angle here too is going to be theta, because this here would be a total 90, so this angle here would be 90 minus theta, and then because this is going to be 90 as well, 90 minus theta would leave us with this being theta as well. Back over here, you would end up with a right angled triangle like this. Similarly, so because this would be a 90 degrees if you continued it here, this would become 90 minus theta, and because this is 90, 90 minus theta leaves you with this angle here, and being theta. Again, if we actually continue it more along this way this time, with your right angle then being up there, just so we have space, this here would end up being your theta, because your RB and your friction, they are parallel lines because they're both horizontal, so the ladder is then a diagonal between them, making these alternate angles. So this is theta, and then the ladder and this component here are parallel, that's diagonal, so they're alternate as well. Okay, so all of these angles here are theta. As we can see with these questions, our annotations get very cluttered very quickly, so you just want to make sure that you are happy with where everything is and that you have covered everything. Now that we have this, we can start to create certain equations. Again, because we have lots of unknowns here, we're going to want to have multiple equations, some in vertical equilibrium, some in terms of moments. When we take the vertical equilibrium, we actually only have two forces acting in the vertical. That's your reaction A coming straight up, and then your weight of the ladder coming straight down. So we can say the reaction A must just therefore equal your 20G. But then how does that potentially help us find the magnitude of the friction? Well, the friction is going horizontally, not vertically. Oh yeah, we can have horizontal equilibrium as well. So mentioning thus far, even though we've only been using vertical, here, because our rod or ladder is now at a diagonal, now we have horizontal forces as well. We can take horizontal equilibrium, so again, if maybe we want to specify, that's vertical equilibrium, the horizontal equilibrium. The only force actually going to the left is your reaction at B, and the only force going to the right is your friction. Yet friction you can express as just your coefficient of friction times by the reaction at that point, so that's mu times Ra, and we know that mu is going to have 0.4, and the reaction at A we just worked out is 20G. Therefore, we can say, both for the reaction at B and for the friction, that's going to equal 8G newtons. So yes, we can label that 8G and label this 8G as well. Now that we have this, now we've found the magnitude of friction, now we can move on to trying to find the angle here. Now we are going to have to take moments. In this case, let's say we were to take moments about A. Okay. Because it is on the point of slipping, again, it's still technically in equilibrium. So if we try to find our expressions for the clockwise, that should equal the anti-clockwise moments as well. For your clockwise, if we're taking A as our pivots, neither the friction nor the reaction A are going to be making a difference because they both have zero distance from the pivot, leaving us with just a component of the ladder's weight and a component of the reaction at B. The clockwise moment is a component of the ladder's weight, but again, because we need it to be perpendicular to the pivot, we're looking at this part of the force specifically. If we're thinking of this as a right angled triangle, because the angle we're measuring here, theta, is here, that makes this the adjacent. We have the hypotenuse, so we can use cos. So we could say that that there could be expressed as 20g cos theta. And that then needs to be times by a distance, and because it's a uniform rod, it's halfway along, that will be 2.5 meters away from A. This is an equal to, again, the perpendicular component of RB. That is going to be this part of it heading top left this way. Because the angle we're measuring is over here, that makes that the opposite. So this is therefore going to be the reaction at B times sine theta. And again, within each times by distance, that's going to be the whole phi. Now we can simplify both of these because we can say that 2.5 times all of this is going to leave you with 50g cos theta. And here we know that the reaction at B is 8g, so times by 5. That's going to be 40g sine theta, which in turn you can simplify even further by just cancelling through by this common factor of g. So you can say that 50 cos theta equals 40 sine theta. Now this we can actually use just to solve for theta straight away. Yet, just in case you want to go around another method, I'll just also show how we're going to deal if we had taken a pivot at B instead. So if we're now taking our pivot at B, this reaction at B here, that's now the only force that's going to be negated. We're going to have to consider all of the other three. To go clockwise is going to be just the reaction at A, because that's going to be pulling it up and around to the top right. So the reaction at A we know to be 20g. However, we'll be looking for this component here. Because the angle theta is here, that makes that the adjacent. So we'll be calling this 20g cos theta. Somewhat similarly to the first statement that we had before. This time, however, we're going to be timesing it by the whole length of the ladder, so it's going to be times by 5. Then this is going to be equal to the sum of the components of the friction and the weight that will be pulling it in an anti-clockwise motion. For the friction, that's going to be this component here. Because we're measuring this to be theta, this makes this the opposite side. Therefore, that component is going to be 8g sine theta, which will then be times again by that distance of a whole 5 meters. And then we'll add that to, again, it's this component again, so again it's cos, so 20g cos theta times by 2.5. Expanding these, you end up with 100g cos theta equals to 40g sine theta plus 50g cos theta. Okay, if you want, you can cancel through by g's. And if you were to move the 50 cos theta over to the left, what would you end up with? Again, 50 cos theta equals 40 sine theta. So it doesn't matter which point you take as your pivot, it simplifies to the same thing. What we can therefore do is divide the cos theta onto the right hand side and the 40 onto the left hand side. So if you remember from just trigonomic identities, sine over cos equals tan. So we'll have that tan theta equals what was there on the other side, which was your 50 over 40. Therefore, theta is the tan inverse of 50 over 40, which, if you just put that in your calculator, make sure you're in degrees, that's going to give you 51.3 degrees. Okay, so again, that's just how, if we kind of have something at a diagonal, we can potentially take components before we start taking moments, because the distance and the forces for the moments have to be at right angles to the rod, the beam, whatever it is. So then, just for our final question, we have a uniform rod AB of mass 3 kilograms and length 2 meters and is held in equilibrium by a light inextensible string BC. So to confirm, so AB here is the actual rod and BC here is just a string holding it in that horizontal position. And we're told that AC is 1.5 meters. So find the tension in the string plus the magnitude and direction of the force exerted on the rod at A. Well, we'll come to what that potentially may mean, obviously, later on in the question. Start off with, let's just focus on finding that tension in the string. And if we're going to do that, again, our first step should always be just annotating. So, what we can say is, because it's a uniform rod, the weight is going to act in the middle. So this 3 kilograms, which is 3 times gravity for the weight, so 3g is going to act here. Where this is then a distance of 1 meter, because half the 2 meter length. You're going to have tension going up the string here. And then, for now, even though they haven't given any kind of indication over here, there is obviously an angle. So let's just call this angle theta for a second. If you want, you could also, I guess, label this as 1.5 meters. So, if we're going to be working with the tension here, we're going to be having to find its components that are perpendicular to the rod. So start at the point where that force does apply to the rod, and then create what would be the perpendicular line, and now we're obviously then going to join that up here, descend, to make that a right angle here. And also, because these are now parallel, that's diagonal between them, alternate angles, that makes this theta as well. Now, with all these thetas that we're starting to put in, and because we're going to have components, like before, we're about to start getting, again, sine theta, cos theta, tan theta, and so forth. But because the question isn't asking us to work out theta, it may be one of those instances that we get in mechanics where we'd rather just get a fractional value for what each of the functions is, rather than necessarily working out what the angle is itself. And what I mean by that is, if we just focus on ABC as a triangle, you have a right angle here essentially, where this then becomes your opposite side of 1.5, and then AB is your adjacent for 2. The angle here, therefore, could be expressed, well, the tan of that angle, therefore, could be expressed as this opposite over this adjacent. So tan theta could be thought of as 1.5 over 2, which would be the same as 3 over 4. Now, if we're thinking of this as a 3 and a 4 for the opposite and the adjacent, because it's a right-angled triangle, just in terms of proportions, you could say, for Pythagoras, 3 squared plus 4 squared equals that third side squared. That leaves the hypotenuse in this proportion having a value of 5. Therefore, sine theta for opposite over hypotenuse, the opposite was well, now the equivalent of 3, so that's going to become 3 over hypotenuse of 5, and cos theta is now going to be adjacent over hypotenuse, so 4 over 5. Again, this is kind of addressed in those other questions in terms of slopes and other static rigid bodies or moving bodies, wherein you may be given a sine theta equals this, and you're just going to then, rather than working out what theta is, just extrapolate what fractional value the other trigonomic functions are going to have. So again, we don't have to work this out. We can now just go, wherever sine theta shows up, just put in a 3 over 5. Whenever a cos theta shows up, just put in a 4 over 5. If that's clear, then yes, let's go back to now trying to work out the tension in the string. For this, we'll start trying to take moments, but we're going to take moments about a pivot of A, because that's where it's fixed to the wall. So pivot at A. In terms of our clockwise moment, that is going to be our 3g here, because that's going to be bringing it down around this way. And it's already perpendicular, so we don't need to take a component of that. So it's just 3g times by a distance of 1. So it doesn't change anything. Here, though, and for the anti-clockwise, is going to be this component of the tension here coming straight up. So that's going to be t sine theta here, because that's obviously the opposite side, and that would be times by the total length AB, which would be 2. Well, the sine theta we know to be 3/5. So 2 times that is your 6 over 5. So therefore 3g equals 6 over 5t. Therefore, you can say that t is going to equal 5 over 2g. So now then, why didn't I use the vertical equilibrium instead to try to solve it? Why did I go straight to the moments? Well, that's because I haven't drawn every single force on this diagram. There's also obviously going to be a reaction force between the wall and the rod. As it's saying, the force exerted on the rod at A. Well, what else is going to be exerting that force other than the wall itself? The problem is we don't know exactly how this force is going to be applying. We don't know if it's going to be coming straight to the right, if it's going to be at an angle. It's probably going to be coming up this way here. But for now, let's just label that F. Okay? But yes, if there is indeed some vertical component to this force F, then this component T here would not equal this weight here. Actually, we can see that. The 3g is not the same as the 5 over 2g. There is some other component at play here. And similarly for the horizontal, we've got some horizontal component of T coming to the left here. And if it wasn't for this F, there'd be nothing coming to the right. Therefore, the rod should be breaking straight through the wall, which it isn't. So, just to complete that annotation, if we also just draw on a right-angled triangle, then per it being a right-angled triangle, we're going to need an angle. So the angle we're probably going to measure is this here because it's the angle at A, but we don't know what that angle is going to be. We don't know necessarily how it's going to relate to this angle here, theta, because as I say, we don't know which way this force is coming from. So we may want to label it as just something else. I'm going to label it as X. Okay. So now we are going to be able to take equilibrium in the horizontal and the vertical. So let's say we were just to do like our horizontal equilibrium first. But what we can say is that we'll have, as I said before, this leftward component of T here. So that's going to become, well, we now know that T is this. So 5 over 2g times by your cos theta, which we know to be 4 over 5. And that's going to equal the rightward component of this here. Now we know neither of F or X, so the best we can just say is that'll be F cos X here. Now, as for the vertical, because we're going to have to shift to another equation in order to get something with which we can eliminate an unknown, that's now going to be that vertical component we identified before to do with T. Again, we now know that T is 5 over 2g. This, of course, then just be timesing by what would be the sine theta, but we know that has a value of 3/5. This would then have added to it the upwards component of F. Again, we can say that with certainty that this is going to be one of the upward forces, because right now the downward of 3g is greater than what this product here is going to end up with. So to be balanced, we're going to have to add more to the upward direction. If we were mistaken though, all that's going to mean is we'd end up with a minus number in our answer, and you can just ignore the minus and say it's happening in the other direction. But here, that component of F here, therefore, is just going to be F and then sine X here. And that equals that downward, as I say, which is just going to be the 3g. So, to simplify both of these, therefore, so we've ended up with F cos X. That's going to equal 2g if you were to times the 5 over 2 and the 4 over 5 together. And then here we've got that the F sine of X, that's going to equal 3g minus, and together this would make 3 over 2g, which in turn, 3 minus 3 over 2, that's just another 3 over 2g. So from here, we can work out what the overall f is going to be, because if we divide these by each other, the f sine x divided by f cos x, the f's would cancel, sine over cos is tan, so tan of x, that would equal your 3 over 2g divided by 2g. That would simplify to just be 3/4. So x is going to equal the tan inverse of 3/4, which is just going to be approximately 36.9 degrees from below the horizontal, if you wanted to be specific about that direction as was above or below. And now, as you may notice now that we have worked this through, in fact, yes, that angle will have been the same as the theta from before, as again the theta of the angle once again equaled that 3/4. Now then, as for working out your F, so the magnitude of the force, right now we only have the direction. We can either just substitute this back into an earlier expression, let's say this one from here. So we could say that F is going to equal 2g divided by the cos of 36.9, or we could use Pythagoras, essentially, to say that if this is going to be an expression of the adjacent, and this is an expression of the opposite, then this squared plus this squared should equal f squared. So you ended up with 2g squared plus 3 over 2g squared, or square rooted. Either way, you end up with approximately 2.5 g newtons being your magnitude of that force exerted on the wall, by the wall on A.